Okay, so I think it's time. Yeah, it's time to start. So today's class will continue to talk about like the GACH model. So first, let me help you to review a little bit this GACH model. So in this GACH model, or right now we just talk about like the ARCH model. Now the GACH, just ARCH. We will talk about the GACH today. So the ARCH model, or sorry to be more precise, the ARMA ARCH model. So what is the ARMA ARCH model? So the ARMA ARCH model is your RT, which is like typically your return of an asset is equal to mu t plus epsilon t, sigma t epsilon t. Okay, and this mu t can follow some ARMA process. Okay, so for example, it can follow like say phi 0 plus phi 1 RT minus 1. Okay. So that's like a AR1 process. Okay. And also the sigma t squared also follows some like AR process or some type of like AR process. So AR. So this is like the ARCH1. And taking this together, this is the AR1 ARCH1 model. So we can include more terms in this model. So for example, you can make this like a AR2 model, or this like a ARCH2 model, or maybe you can have like this a ARMA 1.1 model, or maybe ARMA 1.2 model. So you can have like your model like much richer. And the benefits of why we're considering this model is because we want to capture, basically we want to capture like those clustering stuff in the data. So we find like the high volatile time periods are usually clustered together. So that's why we include this ARCH1 in our model to capture this. Okay, so that's like the setup of the ARMA ARCH1 model. And now the question, or a more practical question, is how can we fit a ARMA ARCH model? Okay. So in today's class, we will basically talk about how to fit this model. So what criteria we want to look at. Okay. So how to fit an ARMA ARCH model. So it basically follows two steps. Okay, so step number one is that we will look at RT, okay, so which is your raw data. So we will look at the RT ACF, sorry, so ACF and the PACF of RT. So we'll look at the ACF and PACF of your RT, okay, and identify an ARMA structure. So this basically is doing this part. This basically is doing like the ARMA part of your big model. Okay, and this is actually easy, right? We know how to do that. We like students pretty much like all our time in our previous class to do that, right? So we look at the ACF and the PACF of the raw data. Perhaps we want to do some transformations here, like the log transformation or the first difference transformation. Then we will identify an ARMA structure. Okay. So for today's, for this class, we won't do like the SREMA here, which is like more complicated. So for this class, we'll just focus on the ARMA structure, but it can definitely be extended to the SREMA structure. Okay, so that's step one. And step two is new. So after we find this ARMA structure, we will basically like fit this model. So we fit We fit an ARMA model to RT, then we obtain the residues. Okay, so we obtain the residues. So let's call it, that's basically like your RT minus mu T, right? So what is your RT minus mu T? Your RT minus mu T is basically sigma T epsilon T. Okay. So we obtain the residues from the regression or the ARMA model. Okay. And here's like a key difference thing. So we then look at the ACF and PACF of RT minus mu T square. Okay. So this is important. This is like residual square. To decide the arch structure. Okay, so when we consider the square, it is because you can see here, once we do the residue, what we obtain is this part, right? Sigma T epsilon T. However, in this arch structure, what we actually have here is like sigma T square. Okay, so we take the square of the residues in order to mimic the sigma T square in the arch model. So that's why we do sigma T, we look at the residues square here. Okay, so everybody follows this. Okay, so that's why we'll take a look at the residual square. Okay. And we will look at the ACF and the PACF to decide the arch structure. So if there is an AR structure, then we will fit an arch model. So what is the AR structure? The AR structure is basically like the PACF cuts off and the ACF tails off. Okay, so if you find like your ACF tails off and your PACF cuts off at leg number 2, then that's an arch 2 model. And if like it's cuts off at leg 1, then that's an arch 1 model. And if there is an ARMA structure, so which means like both ACF and the PACF tails off, then we will fit a gauge model. Yeah, and in our this like very sort of like basic setup, if you find like there's an MA structure, you probably ask like what model I want to fit, and the answer is that you cannot fit a MA structure here. The reason is that it's just not like in math, it just does not work. So you cannot fit an, if you find an MA structure in your residual square, you just probably go with like the gauge model. You just fit an ARMA model to that. Okay, if you like do the R, if you just like ignore the AR part, just fit an MA model, it won't work. Okay, so the math just does not work. Okay. Yeah, the basic reason is that you can see here we only consider RT minus 1. So we're doing something like the AR stuff. The AR stuff is important. We need this. We need this in order to capture the high volatile stuff, or I mean the clustering stuff. All right, so that's the 2 simple steps or 2 basic steps of fitting a ARMA Arch 1 model. But no, ARMA Arch 1, just an ARMA Arch or ARMA gauge model. Yeah, I mean, that's, but you definitely need to fit a lot of models, checking the AIC, the BIC, the significance of the residual, and the significance of the coefficients and the residual plot to decide your best model. Okay, so same idea as fitting a SRAMA model. So any questions first? Okay, So I think if there's no question, I think it's a good idea to look at some examples of this. Okay, how we can do this. So let me switch to R. Save the photos. So let's look at an example. So I think today I want to do 2 examples, okay? So let me first run this library. Okay, so the first example is a GMP. Minimize this, okay. Okay, so that's a GMP from like 1950 to 2000. So we have seen this graph in our very early class, our very previous class, I think class 1, class 2. Okay, so definitely now you know that this is not a very good graph. Okay, so it is first definitely not stationary. There's a very clear trend, might be quadratic or might be linear. And also like it seems that there's some like heteroscedasticity in this graph. Okay, so like the variance here is definitely larger than the variance like along these lines. So what we do is that we will do this 2 transformation. First is a first order transformation, and the second is to take the log. So that's what I got if I do the first order difference transformation plus the log transformation. Yeah, so you can see first, like the stationary part is definitely good. So there's basically no stationary here. The mean is a constant. The thing that is looks like there's still some like heteroscedasticity here. So you can maybe consider other types of transformation, but for the illustration purpose of this example, we'll just go with the log transformation. Okay, so now we will basically like work on this plot. Okay, so right, so we will work on the diff log GMP. Okay. All right, so let's recall our first step. Our first step is to look at the ACF of the raw data. So that's what we got. Right, so you can see that a couple of things, I think you can notice that there are, for example, here you can see the PACF cuts off at number 1. Okay, so that implies we might consider a ARMA, just an AR1 model. Or you can think that the ACF cuts off at 2 lengths. So maybe here we'll just fit a MA2 model, like for the mu-T part, okay? So I think I just go with the textbook. Yes, I think I just go with the textbook and fit a AR1 model to it. And you can check like the MA2 model later, or maybe AR1 MA2 model, AR MA12 model. Okay, so AR2. Okay, so the next thing is that we will get the residues. Okay, so we fit a S ARIMA 100 on the raw data. Okay, and we got its residues. Okay. So that's the residual. So let me write it here. So we obtain the residues from the ARMA, just the AR, not AR, just AR1, sorry, from the AR1 model. Okay. And remember, the next thing that we want to do is that we will calculate the residual square and look at the ACF and the PACF plot of the residual square. And the reason that we want to do the residual square is because the sigma t part in the arch model is basically sigma t square. So we need to take the square of the residues in order to match the sigma t square in the model. So here we do like residual square, and we plot its ACF and the PACF. Okay, so let me write down here. So we plot the ACF and PACF of residual square. Okay, so this is important. Okay, so if you just do the residue, get the ACF and the PACF of the residue, it probably does not work, or it will give you the wrong answer. Okay, so now what model you can get from by looking at the ACF and the PACF plot. So it looks to me, or I mean, it looks like all the lags are within the confidence interval. So that means both ACF and the PACF tails off. Okay, so I actually do not see any like cutoff lags. Okay, but I mean the textbook, because we just like use this example as a illustration. So I think we will first fit a Arch1 model. Okay, so we will not go to the gauge directly, which first fit a Arch1 model. So even though we do not see cutoffs in the ACF and the PACF plot, but I mean, just for the illustration purpose, we'll just assume that this like ACF lag cuts off at 1, and we will fit a AR1 model to it, I mean, a Arch1 model to it, and we will see that this is actually not a very good model. Okay, so let's do this. So the library that you will use for the gauge model is this. You will like install this fgauge package and in your library, and if you want to use it, you just call it library fgauge. Okay. Okay, so this is the data, and now this is the gauge fit. Okay, so let me go over the output with you, and let me first write down what is fits a ARMA 10 Arch1, or let's just call it gauge1. Just call it Arch1. Okay, Arch1 to it. Okay, so this is what the command means. So the data we use is this GMPR, where this GMPR is like the diff and the log. Okay, so the transformation of the GMP data. And the ARMA part is this. So it's easy. So it's just 1, 0. Okay. And the gauge part is 1, 0. So if it's just like an Arch1 model, it's just 1. If it has like a gauge term, like if it has a G term, we will later put some orders here. Okay, but if it's just like a Arch1, it's just like gauge 1, 0. If it's like Arch2, then it is gauge 2, 0. Okay. So I think I just write it more clearly, not to confuse you. Okay, so that's the regression, and now let's look at the output. Okay, so the output is a little bit different. Okay, so first is the coefficients. Okay, so yeah, the coefficients like it gives us is slightly like different from what we usually see. So it has like two parts. The first part is the mu and AR1. Okay, so in the output, mu and AR1 is the coefficients for the ARMA 10 part. Okay, right. So in the ARMA 10 model, we have like this alpha 0 plus alpha 1, I mean RT minus 1. Okay, so this mu is just alpha 0. I don't know why it calls mu. Maybe it's just because it is like the mean of the regression, so it calls mu. So the mu is just alpha 0, and this AR1 is just a coefficient of the AR1 term. Okay. And the second part is this omega and alpha 1. So omega and alpha 1 is the coefficients for the arch 1, 0, or the arch, let's just call it Gauch 1, 0 part. So again, this omega is the intercept, and this alpha 1 is the coefficient for the arch 1, 0. Sorry, for the Gauch 1, 0 model. Okay. Right. So that's how you interpret, how you read like the output. And luckily, we can see that all the coefficients are statistically significant. The alpha 1 coefficient is marginally significant. Now that's good, but it's still significant at 5% significance level. Okay. All right. The next thing that we want to look at is this residual test. Okay. So we will focus on this LB test. Okay. So we'll focus on this LB test. We just ignore the first two tests. We'll just focus on this LB test. It is the test that we use for the S-ARIMA model. So it is basically a test on the R, where this R means the residue, or the R square, which means the residual square. Okay. And we want the p-value to be larger than 5%. Okay, so exactly the same idea we have for the LB statistics in the S-ARIMA model. So if the p-value is larger than 5%, so that means we cannot reject the null hypothesis. That means our model is a good model. Okay, and on the other hand, if the p-value is less than 5%, so that means we will reject the null hypothesis and suggesting that we do have some other better models. So our model is not a good model. So we will look at the LB test, and we want the p-value to be larger than 5%. Okay. All right. And the third thing we want to look at is, of course, the AIC and BIC. Okay, so we will also look at AIC and BIC. Okay. Yeah, and also definitely for the coefficients, we want them to be significant. Okay. Right. So, I mean, just by looking at the output, so I realized that one of the coefficient here is marginally significant, which is not bad, it's acceptable. But I noticed that there are a couple of LB tests that are statistically significant, suggesting that we perhaps have better models. Okay. So what are those better models? So that's like basically the model selection process. So remember what we have. So first, if you still remember the ACF and the PACF of the raw data, go with the AR1, but it is possibly that it's just like a ARMA11. Okay, so that's what I fit here. I fit ARMA11 Gauch 1.0 model. And the reason I fit this model is because I find like the ACF also has some cutoff. I mean, not the cut. I just interpret it as both of it as tails off. I'm sorry. Okay. So that's why I fit a ARMA11. The Gauch 1.0 is this, and I run this regression. Okay, and I think this is not as good as the first one. Yes, you can see like the MA1 coefficients is statistically insignificant. Okay, and I still find like there are a few LB tests that are statistically significant. Okay, yeah, and I think this AIC is gonna be larger than the AIC of the first model. 4. Yeah, so this is negative 4.6 6.47, but this is like negative 4.64. So our first model is definitely better than this model, considering the significance, the LB statistic, and also the AIC and BIC. Okay. Yeah, and I also tried some other models. So this is like the AR20 GACH10 model. And this is what I got. And I think, yeah, this is still not good. Insignificant coefficients, significant LB statistics, and yeah, maybe larger AIC and BIC. Yeah, and just a couple more models, and I realized that just it looks like the AR1 ARCH1 model is our best model, which is the first model. Yeah, but it still has some problems. As I said, it has marginally significant coefficient and the residuals are not normal. So let's change another word. So the LB statistic is significant means that the residuals are not normal. So the LB tests are significant. This implies that the residuals are not normal. Okay. All right, so we can see that that's how we fit like this ARMA ARCH1 model. And from this example, we can notice that it is not a very good model. We have a couple of problems. So what's the question is like, what causes this problem? So as I said, by just looking at the ACF and the PACF of the residual square, we actually do not see that the PACF has a cutoff and the ACF tails off. It looks like both ACF and the PACF tails off. Okay, and if you go back to our like 2 steps, that means we might want to fit a GACH model to it. Okay, so instead of fitting an ARCH model, we might want to fit a GACH model to it. Okay, so now I think I want to just introduce some theories about the GACH models. Oh yeah, first, so any questions about like the ARMA ARCH model fitting, or how to read the output and how to fit the model? Okay, so if no questions, I think I want to talk more about the GACH model. So I'll switch to the whiteboard. Okay, so question. This is type of model specific to certain types of data. Yeah, so good question. So is this specific for certain types of data? Yes. So if you do see like the reason that why we care about a GACH model is because when the economists, when they study like the asset return data, they realize that the variance of the data is not homoscedasticity. Yes, so that's in most cases, it is for volatility, because the reason is that in asset return data, the high volatility tends to be clustered together, and the low volatility period also tends to be clustered together. So that's like the motivation of the GACH model. But I mean, when you look at the raw plot of a data, and if you find a couple of things, if you find like the variance of the data is not constant, and if you find like there is like some clustered, like if you find like the variance of the data is clustered, then you might consider using a GACH model. Okay, yeah, so the motivation for the GACH model is like the finance, but it can definitely be used in other types of data. Okay, so now let's talk about the GACH data. Sorry, the GACH model. The GACH model. Let's just do it. Just do it like ARMA GACH mode. the ARMA-GACH model. So the ARMA-GACH model is a extension of the ARMA-ARCH model. Okay. And the extension part is basically the MA part. Okay, so which I will show you. Okay, so let's first do a pure GACH 1-1 model. So this RT equal to T epsilon T square. Okay. No, what I'm sorry. It's equal to let's do a mu T here. Okay. So that's the GACH 1-1 model. The key difference of the GACH 1-1 model and the ARCH 1-1 model is this term. Okay. Which you can basically think as a MA term of the sigma T squared. Okay, so what we used to have is just this part, this AR part, but now we introduce this MA part. Okay. So that's the key difference, and that's the only difference. I think like that's the only difference in setup. Okay. And why this is useful? This would allow us to capture, basically to capture like the relations between sigma T and sigma T minus 1. So it allows like some correlations there. Okay, and that's why you will see that it will give you a ARMA structure in the residual square. Okay, and we can generalize this definitely to a GACH PQ. Okay. So for the GACH PQ model, similar to the ARCH model, there's no difference in the main equation. Okay, so the return is always written as this. Okay, it's like a mu T plus sigma T epsilon T. It's always written as this. The difference is the second equation. Okay. So this is like a little bit different from the S-ARIMA model. So in the S-ARIMA model, we include some AR part and the MA part in the main equation. But in this GACH model, we do not do anything in the main equation. All the changes happen in the second equation. It's called beta J square sigma T minus J square. So that's the GACH PQ model. And of course, we can introduce some AR parts to this model. Okay, so that would give us 3 equations. So for example, what is like the AR1 GACH 1-1 model? So that is plus mu T sigma T squared. This is going to be exactly the same. Here, the difference is that we have this mu T part, and this mu T part is not just a constant, it follows a AR1 process. Okay, so here it is RT minus 1, not mu T minus 1. Okay, so if you just plug in this back into here, you will see it's like RT equal to phi 0 plus phi 1 RT minus 1. So it's not mu T minus 1. Okay. So that's the AR1 GACH 1-1 model. And of course, you can have a ARMA PQ. Yeah, I think that's not very good notation. So let's use, I don't know, let's use P hat, Q hat. Okay, Gotch. You can have like this very large model. So you can have like the P hat and the Q hat terms in the ARMA part, and you can also have like the P part and the Q part in the Gotch model. Okay. Okay, so any questions about like the ARMA Gotch model, like the setup? Okay. And how to fit this model? Exactly the same step. Okay, so we first fit like this ARMA P hat Q hat part by looking at the ACF and the PACF of the raw data. Then we obtain its residual square. Okay, then we plot the ACF and the PACF of the residual square of the ARMA model fit. Okay, then if we realize that the residual square, the ACF and the PACF of the residual square both tail off, then we will fit a Gotch PQ to it. Okay. So exactly the same step that I discussed earlier. Okay, so now I think let's go back to the R and work on this ARMA Gotch model example. So first, second fold. Okay, so let's go back to this GMP example. Okay, so remember that what I said earlier is that if I fit a ARMA 1,0 model, and after I plot the ACF and the PACF of the residual square, I realized that it looks like both the ACF and the PACF tails off. So that suggests we actually want to fit a Gotch model to it. So how about we start with a Gotch 1,1 model? So yeah, this is like the ARMA 1,0 Gotch 1,1 model. Okay, yeah, and this part, like the conditional distribution, you can have this. It will just tell you the degree of freedom of the t-test, which I will show you later. Okay. So now you can check the results. Okay. So let me copy this. Okay. So this is the Gotch 1,1. Okay. So this is what we fit, and in the output, similarly, mu and AR1 part are the coefficients for the ARMA 1 part, ARMA 1,0 part. Okay. Okay, and this omega alpha 1 and beta 1 omega alpha 1 and beta 1 are the coefficients for the Gotch 1,1 part. Okay, right? Because in the Gotch 1,1 model, we have 3 coefficients, right? First coefficient is the intercept. The second coefficient is the AR coefficient, and the third coefficient is the MA coefficient. Okay, and again, we want all of them to be statistically significant. Okay. But you can notice that the omega and the alpha 1, unfortunately, is not statistically significant. Okay, and also, what is this shape? So you notice that right now we have like a shape here, and this shape is just the degree of freedom for the t-test. Okay, so you see like we have like all this t-test, and the degree of freedom here is just approximately 8. Okay, yeah, so it's not that important, but it just tells you the degree of freedom for the t-test. And if you do not include this part of the command, like the conditional distribution equal to standard, it won't show you this shape. Okay, so it's just an optional like command here. Okay, right. And also for the residual statistic test, we again look at the LB test. So all this LB test, and we want it to be larger than 5%. And you can now notice the difference here very quickly, right? So now all the p-values of the LB statistics now are larger than 5%. So this is very different from the ARCH10 model or the ARCH1 model. Remember, in the ARCH1 model, I think for the last 3 LB statistics, they are statistically significant. But now we have all of them statistically insignificant, which is a big improvement. Okay. And of course, we will look at the AIC and the BIC. Okay. And I remember the AIC for the ARCH1 model is approximately negative 6.47. And right now we have negative 6.55. So again, the AIC for this model is smaller than the ARCH1 model, which suggests that the current model is a good model. Okay. I mean, it's better than the ARCH1 model. Okay. All right, but here we still notice that like these 2 coefficients are statistically insignificant. Okay, so is there any way that we can improve it? So what we do is that we will just, or what I do is just increase the order of the gauge part and see if I can improve the coefficients. Okay, so I run this ARMA10 gauge12 model, and yeah, I notice the results actually becomes worse. So looks like all the gauge coefficients become statistically insignificant. Okay, and also I tried this gauge2-1 model, and I think I have the same problem. Yes, so it does. It seems to me that there's not much improvement. The coefficients are still like insignificant. All right, so just by looking at like all this stuff, like it looks like currently for now, like the AR1 gauge11 model is the best model. The only problem it has is that some of the coefficients are marginally significant. Okay, so we can increase the order of the model to find a better one, or like either in this AR part and also in this gauge part. So we will just try to do like all these steps to find the best model. And of course, you can also take different transformations on your raw data. Currently, we are doing the first order difference plus a log transformation. You can perhaps try the second order difference, or you can perhaps try like some like square root transformation, or maybe, I don't know, some other the more general Box-Cox transformation to find a better model. Okay, yeah, so the logic of the model selection process is exactly the same as what I discussed earlier. The difference here is that we have like this, basically like this 2-step fit. So we will first fit like an AR part, then from the AR part, we will fit a gauge part. Okay. Okay, so any questions here? Okay, so if there are no questions, I think I want to do one more example. So this is the, I think the Dow Jones return example. Okay, so, all right, so here is the ACF and the PACF of the Dow Jones return. And again, we do this, let me first plot it for you. So yeah, so here's like the close price of the Dow Jones from 2006 to 2015. Okay, so again, we can see some trend. It's not stationary, and we can see like some variance. So we will take the log transformation, and we can plot the what's the All right, so that's the plot we will have after the transformation, and we notice that you can see like there's still some like large variance, and also the more important thing is that like the high volatile periods tends to be clustered together, and the low volatile periods tend to be clustered together. Okay, so that implies that we want to fit a gauge model to that. So what we do is that we will first look at the ACF and PACF plot of our transformed raw data. Okay, and this is ACF and this is a PACF plot. So the textbook goes with a AR1 model. Okay, so it says that the PACF cuts off at leg number 1. The PACF cuts off at leg number 1, the ACF tails off. So it goes with a like a AR1 model. And later I just check the AR2 model. Okay, so let's first do with the AR1 model, and let's find the difference. Let's find the residues after we fit this model, and let's plot the ACF and the PACF of the residual square. Okay, so what you can see from here, yeah, so you can see from here that this is very clear. So both the ACF and the PACF tails off. Okay, so I think if you increase the number of legs for the ACF, you will see that the legs of the ACF would eventually go within this confidence interval. Okay, and the PACF is, I think, easy to notice. It's just tails off. Okay, so this suggests that we will fit a gauge 1-1, or a gauge model to it. Okay, so how about we just start with a gauge 1-1 model? And so the big model we fit is this ARMA 10 gauge 1-1 model. Okay, so let's fit this model and see what we got. Okay. So first notice that all the coefficients are significant, which is good. And second, let's check the residual test. And it looks like only one of it is like less than 5%, and all the others are larger than 5%. Okay, so which is also not bad. So most LB tests are insignificant. Okay, and finally, I want to write down what is the AIC and the BIC. So the AIC is negative 6.55, and the BIC is negative 6.54. Okay, so that's model number 1, which looks like not very bad model. Everything looks good except like one of the LB tests is a little bit off. Okay, so well, then how about increase gauge model a little bit and see if I can have some improvements here. Okay, and this is what I got. Okay, so it looks like one of the coefficients becomes statistically insignificant. Okay, one of the coefficients becomes insignificant. And how about the LB test? Yeah, again, like this test, the second test is significant, but it's not that bad, like very close to 5%. Okay, and how about the AIC and the BIC? So the AIC right now is negative, oh, pretty close, 557, and this is 541. Okay, let's go to the third decimal point. Okay. This is 550,536. Okay. Yeah, I mean, just by looking at the AIC and the BIC, it seems like the second model is better, but not significantly better. It only differs in the third decimal point. Yeah, but I mean, one of the coefficients is insignificant, might be a problem. So I mean, from like this two plots, from this two models, it seems to me like the first model might be a little bit better than the second model. Okay, the AIC and the BIC are close, the LB tests are close, but in the first model, all the coefficients are statistically significant. Okay. All right, and as I said, just by looking at the AIC, so the ACF and the PACF of the raw data, it seems that this PACF, it looks like it actually cuts off at leg number 2, not leg number 1. Okay, so what I do is that I change the order of the ARMA part. Okay, and remember, whenever you change the part of the ARMA part, you need to plot the residual square again, right? Because whenever you change like this order from like 100 to 200, the residual is going to be different. So that means you need to replot the ACF and the PACF of the residual square. Okay, so you need to do, you cannot like just change the coefficient in this final regression command and just use like this residual square plot. This is not correct. This is not the correct residual plot because you change like the ARMA part first. Okay, so let's do this and look at the residual square plot. Okay, so the ACF and the PACF plot of the residual square again suggests that this looks like a Garch model. It's definitely not Arch model because we see both ACF and the PACF tail off. Okay, so I go with this ARMA 2.0 Garch 1.1 model. Okay, and this is what I got. So let me see here. So let's first check the coefficients. It looks like the AR2 coefficients is insignificant. Yeah, this is actually very, I don't know, I mean, this is very informative because the difference between this model, what we just considered, and this ARMA 1.0 model is that we add a AR2 part to it. But unfortunately, this AR2 part becomes statistically insignificant. So this should be somewhat, I mean, informative, telling us that the AR2 part should not be included in the model. Okay, and I guess that's why the textbook goes with AR1. Perhaps it's also tries this AR2 and realize that the AR2 is not very good. Okay, so and for the completeness purpose, let's just check like all the LB statistics. And it looks like it's not very good. So you can see like the second LB statistics significant. The first and the 3 are marginally significant. It's definitely insignificant at a 10% significance level. Okay, so some of the LB tests are significant. Okay, and finally, what about like the AIC, the BIC? So the AIC looks like it's negative 6.550, BIC negative 6.534. Okay. All right. So yeah, I do not see much difference between the AIC of this model, the AIC BIC of this model, and the AIC BIC of the first model. But I can just tell from like the AR2 coefficients become insignificant and some of the LB tests become significant to tell that this model is definitely not as good as the first model. Okay. Okay, so I conclude that ARMA 1.0, Garch 1.1 is the best model. Okay. All right, so any questions about like the model fitting? Okay. All right, so if there are no questions, I think I want to talk a little bit more about the restrictions of this Garch model and talk some about like the extensions of that to finish the Garch model part. Okay, so let me switch to the whiteboard. some restrictions. The first and perhaps it's the most significant restrictions is that the Gauch model has like this square formula, right? So sigma t square is equal to like alpha 0 plus alpha 1 RT minus 1 square. So it has like this like square setup in the model. So that means the positive and the negative returns basically have the same effect. Okay, so that's the Gauch model. Assumes positive and negative returns have the same effect because the sigma t squared depends on RT minus 1 squared. Okay, so that is t squared equal to so you can see this is like RT minus 1 squared. So no matter or so for example, like in the last period, you earn like 5%. The effect of this positive 5% earning is basically the same effect as the negative 5% earnings, right? So this actually is not very attractive. Okay, so we actually want like the positive and the negative returns to have different effects on the next period return. Okay, so one way to generalize this, one way to generalize Gauch is to consider the asymmetric power Gauch. Yeah, so there are a lot of like extensions of Gauch. Like each one tries to deal with some of the Gauch problems. Okay, so what is like the asymmetric power Gauch? The symmetric power Gauch is written as this. So mu t plus sigma t epsilon t. Okay, so this is delta. Okay, so not to the power 2, but to the power delta. Okay, alpha 0 plus so this is gamma j, which is the coefficient of RT minus j. Okay, so that's the asymmetric power Gauch. So why it is called power? Because, sorry, this is Q. Okay, so why it is called power? Because you can see the power here is not 2. It can be anything. It can just be delta. So we just call it delta. Okay, and we can actually have some like the algorithms to choose delta. So that's the power comes from, and why it is called asymmetric. Why it is called asymmetric? The symmetric part is actually come from here. Okay, so you can see before what we have before is this alpha j RT minus j. Let's just do it 2, right? But now, and this is like not symmetric. I mean, this is symmetric, okay, and which we discussed is perhaps not very good. So we want to make it to make it asymmetric. We want like the positive return and the negative return to have different effects on next period return. So what we have here is the absolute value of previous period return minus some coefficient rj, gamma j, RT minus j. Okay, so that means what? So if gamma j is positive, yeah, this is the coefficient you will estimate in your model. It's just like the alpha and beta. So if the gamma is positive and your let's say RT minus j is also positive, then what's the effect of RT minus j on your sigma t? then the effect becomes RT minus J minus gamma J RT minus J. So it's just 1 minus gamma J RT minus J. Okay. And on the other hand, if your RT minus J is negative, what you will have? So what you have is negative RT minus J minus let's see, gamma J RT minus J, right? So there's going to be negative 1 minus RJ gamma T minus J. Okay. Right, so you can see that if your return is positive, then effect on next period return is 1 minus gamma J. Okay, so it's like actually becomes small, right? Because we assume gamma J is larger than 0. So like 1 minus something larger than 0 going to be like, say, let's say if it's 0.2, it's 0.8. Okay. However, if your first period return is negative, okay, then what's the effect of it on your next period return? It's negative 1 minus RJ. And let's say let's just pick RJ equal to 0.2 again. Then that effect is negative 1.2. Okay, so it's actually larger than negative 1. You see that? But if it is positive, then it becomes smaller. It's just 0.8. Okay, so which perhaps makes sense. So if your first period's return is negative, then you maybe become like less confident about like your investment. Okay, then that might cause you like maybe lose more money period. Okay, and if you first period return is positive, then you might think, I don't know, like you might become I don't know, some mental stuff and cause you like maybe invest less or some stuff like that so your next period's return gonna be like smaller than your current period return. Okay, but anyway, the difference here is that the effect of current period return on next period return is actually not symmetric. It is actually asymmetric. It depends on your gamma J, and it also depends on whether your first period and next period return. It also depends on whether your first period return is positive or negative. So it depends on a lot of things here. Okay, both gamma J and the sign of RT minus J. Okay, so this is the let's see. This is the gauge. This is the asymmetric gauge. All right, so that's number one, and there are some other restrictions of the gauge model. Okay, so just very quickly go over those restrictions. So first, to estimate the model, we usually want n to be large. Okay. Otherwise, the likelihood is flat. So n is a number of observations. So that's why, again, another reason that people like to use a gauge model for the asset pricing. So for example, if you use a gauge model to study the stock price, to study the stock return, and you know, like the stock price can actually go to like the milliseconds. Okay, so that means you will have basically a very, very large data set. So that makes your gauge model more reliable. But if you use like the gauge model to other types of data, especially like to those, I don't know, like the monthly data or the yearly data, it perhaps does not work very well, because like in those data, like your n is usually not that large. Okay, so that's a second restriction. So we want the n to be large, otherwise like the likelihoods of the estimation is flat. Okay, yeah, and number three, so the model tends to over-predict volatility. Because they respond slowly to large isolated returns. So that means if your return in some periods becomes very large, then it will predict the return in the next period would also be large. Okay, and the 2 periods later would also be large. But this now might be the case. Okay, so in reality, the volatility might go down very quickly, but this Gauge model will predict the volatility won't go down very quickly. And the reason is that it responds very slowly to large isolated returns. Okay. Yeah, that's also a problem of the Gauge. Yeah, and I'm not sure, but I'm pretty sure. Yeah, but I think there are definitely some other models or some other extensions of the Gauge models that can deal with this. Okay, so that's some restrictions of the Gauge, and if you are interested in it, if you want to maybe take, I don't know, more advanced finance classes or even econometrics classes, those more advanced Gauge models will definitely be presented there. Okay, so any questions? Okay, so if there are no questions, I think I want to use the last maybe 10 minutes to do quiz number 7. So let me switch. So let's have another 30 seconds. Okay, so I think I will, okay, good. I think I got all your answers in, and Yeah, it looks like everybody got the correct answer. So gonna be A. And I want to talk this actually a little bit more. So I actually write some codes. Okay. So let's see my R code here. Okay, so this I use this data, CMOS mortality data, and this is a code for ARMA 011012. Okay, so if I run this, this is the thing that you will get. So it will give you a MA1 coefficient and give you the seasonal AR1 coefficient. Okay, yeah, but some of you, or I mean, not you, but some students might think, okay, because this is like a seasonal 12 model, right? It's like the seasonal part is AR1, like, so the seasonal part is like the AR1, sorry, the AR with lag number 12. Okay, so why I cannot write it as a ARMA 10 model, 12-1 model? So why not? Because if I have if I move like this seasonal part, I mean, maybe to the left-hand side of the equation, it becomes a AR12 model. Okay, so why can I just use like this 1201? Okay, it looks like they are equivalent, but actually they are not. So if you run this, then this is a coefficient you've got. You've got the coefficient of AR1 all the way to AR12, okay, and MA1. So, but what we actually need is just like this AR12 coefficient. We will restrict the AR1 coefficient all the way to AR11 coefficient equal to 0. But if you do not tell R to do this kind of the restricted regression, it will provide you the coefficient of AR1 to AR11, which is something which are the things we do not want. We only want the coefficient for AR12 and MA1. And this can be done if you just use this command. Okay. All right, so that's question number 1, and let me do question number 2. You can go back maybe to check your notes. That's a coefficient for. let's have another 1 more minute. Okay, I think I will stop the poll. Okay, so, all right, so the answer is going to be 0.5. 0.5. So the reason is that WT minus 13 is not free coefficient. It is equal to WT minus 1 times WT minus 12. Okay, so you can just go back to your notes and you can see this. So WT minus 13 is not free. It's not a free coefficient. So if it is equal to 0.25, it's going to be equal to WT minus 1 times WT minus 12. So it's like 0.5 times 0.5 equal to 0.25. So the coefficient for WT minus 12 is 0.5. Okay, so that's the second question. So any questions here? Okay, so I think that's it for today's class. I will see you next week.